Hello, welcome to another lesson. Now, in the last lesson, we covered complex numbers. However, some students, especially the younger students at my school, had a certain problem. They did not understand what theta was, or rather, what tan was, and how it worked, or rather sine and cos as well. Now, I've made this video in supplement to that video, but it is still very distinct and generally does not encroach upon the same subjects other than the very concepts of sine and cos. Now, in essence, this video will deal with trigonometry. Which has the word tri, and I will assume that means that it deals with triangles. Rather, one can assume that. I'm not sure about this, but we make use of a lot of triangles, so it's fairly an accurate guess. Now, before we get into trigonometry itself, I will introduce the concept of radians. Now, imagine if we have a circle. A radian will be an angle, theta. Or rather, a radian is a certain ratio which represents an angle. Now, in this regard, let us talk about what this ratio is. The radian is the ratio between the arc of a circle, for example, this arc, its length, so say 2 pi r divided by whatever portion of the circle that is, over the radius of the circle, r. Now, as you can see, this deduces to 2 pi over x. In essence, what a radian is, it is the ratio, or rather not even the ratio, well, it is defined by a ratio, but you can think of it as the portion of the sort of angle sweep in comparison to the whole angle, in a way, I suppose. For example, if we take a fourth of this circle, as it is present here, if this is 90 degrees and the whole thing is 360, then this arc will correspond to 2 pi over 4, or pi over 2. Similarly, if we take 2/3 corresponding to this angle, this will correspond to 2 pi over 2 over 3. No, sorry. Sorry. I seem to be making a mistake here. Divided by, would that be 3 over 2? Well, in essence, wow, I did not expect to make this mistake. Sorry, if I can only have a second. This would correspond to 240 degrees, and respectively 4 over 3 pi. Now, how you ask? Well, it would correspond to 3 over 2, meaning 4 over 3 pi. This would be because compared to, or when we take the whole circle, it is 3 over 2 larger than this small portion. I believe this would be the case, unless I'm mistaken. Well, anyways, essentially, you can think of it as 2 pi multiplied by whatever ratio of the circle's angle you're sweeping. So in this case, 2 over 3. 4 over 3 pi. This is how I think of it, although some teachers prefer to teach it in such a way. Now, this, as you can see, corresponds reasonably well to an angle. if you have, for example, 90 degrees, and you double it, you get 180 degrees. Similarly here, if you have pi over 4, or rather 2 pi times 1 over 4, which is equal to pi over 2, being equivalent to 90 degrees, and you double it, you get pi. And that corresponds to 180 degrees. In essence, 2 pi corresponds to 360 degrees. Now it ought to be said that radians, since they are, as shown before, a ratio between radius and radius, the units cancel out, and therefore they are unitless. Now, in essence, we can think of this as another way to say degrees. And I only bring this up because in prior, I had used radians in lieu of degrees. And yes, and I should further mention that if you wish to find out how many radians a degree is, you use the conversion factor. So 2 pi divided by 360, and say you have, that's equal to 1 degree. Thereby, and if you calculate that, that is roughly 2 pi divided by 360. 1 degree is roughly equal to 0.01745 radians. Or alternatively, you could do 360 degrees divided by 2 pi, and you would see that this, corresponding to 1 radian, would be equal to roughly, I believe, 57.3 degrees. Now that we are done with radians, we may move on to the real topic of this course, or rather this lesson, trigonometry. Think of a triangle. That is a poorly drawn one. Think of a triangle, specifically, with a 90-degree side. Now, if you have an angle here, it will be the case, and always, such that this side will be another angle that is complementary to the side A. Or rather, angle B will be complementary to angle A. And therefore, this triangle, in having 3 known angles, will always have the same ratio between its sides. So, if I have, say, 50 degrees here, and although this won't be correct, and I have, rather, I can make this correct. Why am I using this example? That is a poorly drawn triangle once again. I apologize. If I have 60 degrees here, and say 30 degrees here, and this of course being 90, we always know, and this is always the case, that the side opposite to the 60 degrees, we will for now ignore the 30 degrees, and the side adjacent, so op standing for opposite, and the side adjacent, add, I believe that has 1D, ADG, standing for adjacent, have a constant ratio. So, op over adjacent is equal to 1 over root 3. Or actually, I apologize. This would be root 3 over 1. This will always be the ratio. And now, we may further discuss another matter. For these similar triangles, we can make a specific case wherein, if I may have a moment to think, if we consider a special case of this triangle, wherein one side is root 3, one is 1, of course the angle 60 being here, 90 being here, and this side, through the Pythagorean theorem of root 3 squared plus 1 squared being equal to 2, you would get the following triangle. Now, always, in this case, these two sides will be of the same ratio. But in a special case, wherein we have these exact side lengths, we may consider, in a way, the adjacent side and the opposite side individually. Now, for this specific ratio, we have a function before we get to the individually adjacent and opposite sides. Tan of theta, theta being the angle, is equal to the aforementioned ratio, always. So the tan of 60 in this case is always equal to root 3. And we know that that is the ratio from now on. Now, as I said before, for this case, and it is more so a function than anything else, we have a certain ratio between these three sides. And as we know, we further have the hypotenuse, which also is in ratio with these sides, as it is a similar triangle. Now, the opposite and adjacent sides have this ratio, yet we have another ratio, the one between the hypotenuse and the opposite side, and the one between the hypotenuse and the adjacent side. This being sine and cosine, respectively, represented by the functions sine of theta and cosine of theta. Now, sine of theta would be the opposite, in this case corresponding to root 3, over the hypotenuse. And cosine of theta would be the adjacent, represented by 1 in this case, over the hypotenuse, 2 in this case. So for the angle 60, the sine of 60 is 1 over 2, or, oh, I apologize. It's root 3 over 2. Whereas the cosine of 60 is 1 over 2. Now, these functions of sine, cosine, and tangent are all constant for a certain number. They do not change because they are ratios for similar triangles, regardless of if you multiply all of the sides by the same number, which you must do if you wish to retain the same angles. These will be the same. Now we get to a further matter. The actual shape of these functions. The sine function, if you take all of the angles from 0 to 360, and even beyond that, or less than that, we once again get back to the circle. And think of the circle as starting here and going in such a way. However many revolutions is needed. Now, this specifically is called the unit circle. It is a tool and not really a specific thing. Say you have a circle with a radius of 1. Now, you have some angle theta. Now, corresponding to this angle is the radius 1, its horizontal component, and its vertical component. the horizontal component in this case will equate simply, this will be theta, by the way. The horizontal of theta will simply equate to the opposite over 1. But we know that anything over 1 is itself, so it's sine of theta once again. So here, the vertical component will be the sine of theta, and it is a very similar concept to the with cosine, wherein the horizontal component, sorry, I had erased on, being this, will equate to cosine. Now, when regarding the unit circle, you may see that it also has negative axes, as here, below here, and on this side. Now, when it comes to negative axes, say, for example, we start from here, and we go 270 degrees. So let us say the sine of 270. Now, in this case, it is, I suppose, quite an interesting case, wherein, 270 might be a bit too much for this course, because it will have to do with limits in order to see how we get it. We will once again say an equivalent to 60 pi. If we take 60 pi from here, and we have the 180 from here, this will be a total of 240 pi. I apologize, I'm receiving a call. However, I will shortly return. Now, this will correspond to 240 pi. Now, however, we see that although this triangle behaves similarly to the 60, in that it shares the horizontal components here, being the cosine, and the vertical component, we see that these have negative magnitudes. And thereby, we once again have the same sign, or at least the same magnitude of sine for 240, being root 3 over 2, except this time, the hypotenuse obviously is positive, but we know that the adjacent, or yes, this would be the adjacent, is negative. So we have negative 3 over 2. Similarly, we have cosine of 240, wherein the adjacent side is negative. So we have negative 1 over 2. And in this, we can see that based on the, I suppose, the region within the plane, whether it falls in region 1, 2, 3, or 4, you will get a different combination of negative and positives. And it should be mentioned that thereby, in the top regions, wherein the vertical component is positive, sine will always be positive, whereas in the leftward regions, wherein the horizontal component is always negative, cosine will always be negative. Now, furthermore, we had established that tan is equal to opposite over adjacent. We can write this in a different manner. Tan is equal to opposite over adjacent times r over r. R being the radius, or in this case, the hypotenuse. It does not really matter. Now, thus tan is equal to op over r all over ADG over r. Now, if this reminds you of sine and cos, well, then you're correct. Sine and cos. So therefore, we can see that tan is equal to sine and cos. Now, I have neglected to put the theta or the brackets here, but it retains the same meaning. And furthermore, in areas, now, based on this, we can see, for example, in the quadrant 3, wherein both sine and cos are negative, as they are both negative for tan, tan will be positive, since it's a division of a negative number by a negative number. And similarly, in quadrant 1, 10 will also be positive, since they're both positives being multiplied and divided. However, in regions 2 and 4, in 2 specifically because cosine is negative and sine is positive, tangent will be negative. And in 4, because cosine is positive and sine is negative, tangent will also be negative. I hope you've enjoyed this lesson. I certainly have. Once again, I apologize for the rough quality of the work. I'm still learning on how to do this. Thank you very much for listening, and I hope you've learned something.